So, do the straws and balloons, if your balloons work, does that help? Okay, so what I've got up here is a test lung. So, with the test lung, I essentially have something that might show up. I've got a balloon. It's going to inflate. I've got airways. And airways can have resistance. For instance, if I could get that to point the right way. So that one, does that have a lot of resistance, do you think? I'm a trained professional. So I got a couple of different size lumens, right? If you look down the barrel of these, which is confusing to try and do that, but I've got different resistances here that we're going to be able to look at, and I've got different compliances. So the springs on these things are going to generate an elastic recoil. So we're going to be able to play with compliance. So I need to have Trevor and Deanne, come on up. Oh, and I need Eric and I need Caitlin. So one of you is going to be over here. So you can get around that without... Trevor, I'm going to have you grab this bag. I'm going to have you stand here and hook it up to that. There you go. And Eric, I'm going to have you and Caitlin come around this side. Because we're doing science, right? Which one of you wants the prestige of having this draped around your neck? Okay, there you go. It's prestigious. So your job is going to be start, stop, reset, and you're going to be looking at expiratory time. So you're going to be timing it. You're responsible for recording everything.
I can do that.
You've got good penmanship? Okay. So your jobs are very complicated. You can drop the little green hose. That's not going to be a problem. You're going to be timing one and then the other. Right. So we've got lung 1 and lung 2, right? So we're going to compare those. We got lung 1 and lung 2. We have baseline pressure, tidal volume, end inspiratory pressure, compliance, expiratory time. We're going to put this on a spreadsheet when we get done. But as he starts writing stuff down, you might also start thinking about what are you going to do with all these numbers, right? Now, in order to calculate resistance, what things do you need to know? You need to know flow. Well, we don't have anything on here that'll measure flow. We might be able to measure some pressures, and the pressure that we're actually going to be measuring is going to be alveolar pressure. We're going to measure the pressure in the end, alveolar pressure, which is at the end of the straw. So we're kind of making a connection here, aren't we? Because it's a system.
And inspiratory, right?
And inspiratory, right. So you'll notice we have pressure manometers on here. Got pressure manometer for lung 1, lung 2. Can you read those a little bit?
Yeah.
Is that better or worse?
Better.
Better, okay. So what I want you guys to do is calibrate your hands. Just give that thing a squeeze. And you notice that we've got a volume scale on the back. So yeah, right there. So what I want you guys to both do is try and squeeze that thing up to a liter. Okay, and when you get to a liter, I want you to hold it. Okay, Trevor's a little short. You're going to have to stair step a little more gas in there, a little more. Let it go for just a second, and then squeeze it again, Trevor. This is science. Are we pretty close? Okay, so we've got volume is 1 liter for each one of those lungs. Can you read those pressures, the alveolar pressures? Trevor, you got just a little bit of gas short there, but, so can you read those pressures? So lung 2 is at how much pressure? 18 or 19, okay, and Trevor's, looks like he's lost maybe a little. 15, okay, but they're close enough for government work, right? So what we're going to do now is I want you to go both back to 1 liter, and you're going to time lung 1. So on 3, I want you to let them go. 1, 2, 3. How long?
1 second.
About a 1 second exhalation, okay? I want you to go back to 1 liter and let go on 3. 1, 2, 3. How long? What? It's prestigious. You got to be really good with it. So is it a reset over there? Start, stop, stop. Okay, there we go. It's technology. Okay, so go to a liter, hold it, and then on 3, let it go. 1, 2, 3. How much?
Oh, 1.3.
1.3. So do it one more time, and I want everybody to watch those 2 lungs. Go to a liter, a little more on lung 2, a little more, a little more, a little more, a little more. Okay, let them go. Which one emptied faster? Why?
Less resistance.
Probably it's less resistance. Now, the compliances ought to be pretty similar. The volumes were both a liter. Those alveolar pressures were really pretty close. What was the baseline pressure, Eric, that they started at? Can you read the manometers? Take a look at the manometers and see what the baseline pressures are. Yeah, they both started at 0. So this is like you guys starting off with no pressure in your alveoli at FRC, right? If you had pressure in your alveoli, you'd have flow one way or the other, right? Okay, you guys have done very well. Go put some ice on your hands and forearms. You're a scientist. You're not done yet. You've just started to get good with a stopwatch. Let's have Casey and Maddie come up.
How do you measure pressure? Is it torr or is it
Centimeters of water. Yeah. So we're going to do study number 2 now.
Do we have to be over there?
I'm going to have one on one side, one on the other side. Just give it a squeeze and see what it's like. Okay, so you can get a liter. Can you get a liter? Yeah, pretty close. So, burritos for breakfast? That's okay. Okay, so what I want you guys to do is go to a liter again and hold it. And Eric is going to be measuring the end inspiratory pressures. I've got to get you right at a liter now. Equal volumes. Come on, Maddie. Okay, and then I want, can you read those pressures?
20 on 2?
20 on 2. What was the pressure on lung 1?
Not 65.
About 65. Why is there such a big difference between this pressure on lung 1 and pressure on lung 2? Increased elastance and decreased compliance. If it takes more pressure to generate that volume, you've got a lower compliance. Absolutely. Okay, so now we'll time again on exhalation. So I want you to go to a liter and hold it, and then release on 1, 2, 3. Tell him he's the recorder. That was for lung 1. Okay. And then go to a liter again. And 1. Oh, we got to start over. Get a liter.
Is this number 2?
Yeah, we're going to be doing 1, 2, 3. 2 seconds. Okay. Now I want you to just switch, but try not to bump the lung. And I just want you to feel, or you can pass them if you want to and crisscross them and get confusing. So now give it a squeeze and see what you feel, because I want you to feel this. Takes a lot more pressure, right? Absolutely. So yours doesn't really take much pressure, right? Your lung is more compliant. Lung 2 is the more compliant lung, right? So why did lung 2 take longer to exhale? Kristen, what do you think? The volumes were the same, right? Because they blew them back up, both of them up to a liter. Okay, there's a difference in resistance. So if you have less resistance, shouldn't you get your gas out faster? Was there a difference in elastance? Absolutely. So the one with more elastance wants to empty faster. Good job. Go rest your forearms for a little while.
We're still at 0 on it.
Yep, we're still at 0. Let's have Chelsea and Lena. And just give them a couple of squeezes and see what you perceive. So I want you to squeeze both of them really fast. Okay, it still takes longer to fill the one with more resistance, right? It's like you trying to blow your balloon up through a straw. It's going to take longer to get gas in and longer to get gas out. So if it's an exercise situation, you're going for a run, you're increasing your respiratory rate, that's going to have some implications. So what I want you guys to do is, what's a normal respiratory rate? 12 to 20. Okay, so do you think when you guys exercise, you breathe 20 times a minute when you're really working? What do you breathe? Good answer. Good. Do you think 30? Okay, so we're going to go back and think about total cycle time. If you're breathing at a respiratory rate of 30 breaths per minute, there's 60 seconds in a minute. You've got 2 seconds to get gas in and out, right? Everybody happy? So we're going to go 1 1,000, 2 1,000, 1 1,000, 2 1,000. And I want you to be able to get gas in and out in 2 seconds. So on 3, is this going to work? On 3, I'm going to have you go 1 1,000, okay? 1, 2, 3. Squeeze. 1 1,000, 2 1,000, 1 1,000, 2 1,000, 1 1,000. Chelsea. 1 1,000, 2 1,000. What's happening? What's the difference between these two lungs? So one's not keeping up. Why don't you relax for just a second? Look what Lena's lung just did. Kept exhaling, right? So let's go back and watch the difference again. You ready for that same rate? 1, 2, 3. 1 1,000, 2 1,000, 1 1,000, 2 1. These guys just don't quite. But you can see what we're trying to illustrate here, right? With exercise, the lung with the longest time constant, what happened to its volume? Did it ever exhale? Didn't exhale. So we got a situation with air trap. Well, if you guys want to feel what that's like, everybody, you don't have holes in your straw. Your balloons might be toast. But if you want to see what that feels like, breathe at that rate through your straw. Just don't spit on the person in front of you. Do that. You can have 2 if you want a right main stem and left. But I want you guys to breathe like that. So pitch your nose. 1 1,000, 2 1,000, 1 1,000, 2 1,000. In and out in that same period of time. And I should have been drum major or something, because do you feel your lungs filling up a little bit because you don't have time to get the gas out? Yeah, that's what dyspnea is. That's what shortness of breath is. Not that people who haven't exercised or have exercised haven't felt that, but the time constant of that lung with higher resistance, it takes longer to get gas in, but especially longer to get it out. And if you don't let it get out, you're going to air trap. So what was happening, and I'm going to go back to, I want to say Rachel. Is one in a row. Rachel, what happened to Lena's lungs FRC? Absolutely. FRC is the resting expiratory volume. Well, she didn't get down to her normal FRC until she quit exercising and went, right? Okay, good. So you guys can take a rest, and let's have Claudia, and we're going to have you come up, Miss Segal. Segal, right?
Segali.
Segali, that's close enough. Now you're going to have whichever, once you take that long, and go ahead and give them a squeeze. So what do you feel?
Resistance.
Is it resistance or is it just hard to squeeze?
Hard to squeeze.
It's hard to squeeze. So resistance lives in airways, right? Is yours a resistance problem or a compliance problem? It's a compliance problem. So if you think about alveoli that have low compliance, what do they want to do? Yeah, they really want to close, right? Because they really have high elastance. So if you've got alveoli that really want to collapse, they aren't going to have any oxygen left in them. We're going to have somebody who's hypoxemic. They're going to have low oxygen in their blood. So what can we do to try to prevent that collapse? Eric? PEEP. PEEP. We're going to use PEEP. Would you put that PEEP valve on the tray there on her bag? And you've got that little deflector that you've got to take off the top of the exhalation valve. Okay, and then what's your PEEP set at? Try to get it to about 10. Okay, so give it a breath, both of them, and let it go. So you can see that this one is going to a pressure of 10 during exhalation, right? So Eric, the baseline on this study for lung 1 is 10. Do you think it looks like we're pretty 10? Okay. Baseline for the other one is still 0 because we don't have any PEEP. I want you guys to both give a liter of volume. You got to look and see if you're at a liter. Really look at that. Oh, come on, Claudia. Okay, so what are the pressures that we've got in the alveoli when you hold them in a liter? Okay, they're not quite equal. We got to get them equal. Okay, equal volume, close. Hold it. What are your pressures? Lung 1 is 70. Lung 2 is 20. Okay, so squeeze them both to a liter. We're going to do the expiratory time again. Give them a squeeze and hold it and let go on 3. 1, 2, 3. How fast did that first one? 0.65 seconds for lung 1 expiratory time. So go to a liter again. And 1, 2, 3, let them go. 1.3, okay. So still, yours has the longest time constant, for sure. The PEEP didn't really change it very much. It really didn't impact expiratory time very much. Good job. You guys can go rest. Yep. Okay. So we're going to go, enter some data. So we got lung 1 is blue, orange, purple, blue and orange, purple, Got it. So Eric, you guys can enter data.
This is about this page.
It is on my job description.
Here's a Canadian quarter. I knew find a way to get rid of that. So let's go in milliliters, because most of the time with compliance, we're using milliliters per centimeter of water, but it could be liters per centimeter of water, because compliance is changing volume over changing pressure. You guys that have water bottles all have some volume of water in it, right? In mils. Liters. They're both water. God, look at him go.
I know.
Look at him.
Stand back.
That's right. Let you work.
Baseline 50. Oh, come on.
God, I picked the right guy for that job.
Ooh.
Whoa. Ooh. Oh. Ooh.
Mistype.
That's a different class.
Should be it.
Yeah, it should be. Now, I don't know why it's not calculating, because I set this up in the office, and we should have B3, which is change in volume, divided by the difference between end-ins per Oh, I see what we got. We got these two mixed up.
Oh.
So that's okay. We're just going to put it. Baseline is 0. Here we got 15. We should have. Oh, maybe it is. Maybe it doesn't like units. It's not a Unitarian.
Oh, it's not going to pass this class. There it is.
She's not just another pretty face, I'll tell you that. So if we can do that and get rid of the units.
I imagine that's the only time we'll hear you say that.
Yeah, that's like blasphemy. Would you get rid of units on those for me,
Sure.
please? And then we got to have baseline is
Switch
whatever
them.
the lowest is. Yeah. So if you guys are following along, this thing is just doing the calculations of compliance and resistance. Or excuse me, not resistance. Compliance and expiratory time is telling us something about the time constant. Resistance we can't calculate because we don't have flow. Right? Now, I need the young lady in the Bronco hat to come up because I don't know your name, and this is the only way that I can try to learn it.
Abby.
Abby, okay. Well, Abby, you
Just switch
as
this.
a human being tend to have two lungs.
70.
You haven't had one removed for years of heavy smoking, have you? Okay, not yet. All right. So yours now are hooked up together. And we've got a little
And
bit of
15, that
difference
was
in
good.
mechanics between them. I haven't changed it from what we had before. looked at just individual lungs. So what your job is going to be is just to give that a squeeze. And I guess we'll have to have just if you can reach in and give it a squeeze. And try to just give it a real good squeeze.
Ooh.
Try and drop this in so we can just look at pressure manometers here. If you can see those when we get back to the screen.
Oh, what'd you do?
I guess we're going to go back to Doc.
There it is.
Oh, that's why. It's because
Okay.
it's so long.
Give it a real
Went
good
into the other
squeeze.
one.
What do you guys see happening? What do you see happening on lung 1? I don't know.
It's faster.
It's faster, but which one gets to the largest volume right away? Okay, the lung 2 seems to, so give it another real quick squeeze and let it go. Okay, so one of them seems to fill faster, but when she squeezes it and then does a breath hold, what do you see? What happened? Let it go, Abby. And you do another squeeze and hold. What happened to the volumes?
Just. Let's
I
go.
don't think that we have
I mean,
minus 50. 0. There we go. But what did you see in that lung?
There's a pressure gradient between one lung to another. So you
Right.
went from-
So we said one of these lungs tends to fill fast, but not to very much volume, right? The other one is slower to fill, but when we do a breath hold, why is volume being redistributed from one lung to the other lung?
the pressure on one pushes it.
Right, because if you do a breath hold, pressures have to equilibrate. So if you started with more pressure, give it one more squeeze for us, please, Abby. Yeah, why don't you give it a squeeze and hold and see if you can keep your arm down just a little bit so we can look at those two pressure manometers. Now, when she's holding it, they become equal, right? They equilibrate. So let it go and give it a fast squeeze again.
I like that.
Yeah, and a fast squeeze. So this one jumps up first. It fills faster, but to less volume, and then we redistribute things based on pressure. You redistribute or have flow based on pressure. Now, this actually happens in diseased lungs. We have 300 million alveoli, and they're not all the same mechanically, right? This is a thing called Pendeluft. It's a German thing. It's like dirigibles or something that they use in Germany. But it's a redistribution of volume based on the mechanics of one lung or an alveolus compared to another one. Good work. So when we're looking at, you guys have done very good work too, by the way. You guys can go rest. Put your... Thank you for doing the recording. And that should be 10, that should be a 7. So we had equal volumes all the way across, and that simplifies things for us. We could do different volumes. It really isn't going to make much difference when we do these because we go back to wherever I put my, there we go. We're saying that we have a pressure-volume relationship in the lung, right? At low lung volumes, it takes potentially a lot of pressure to open up a lung. Then we get into a stretch where we've got a straight line. So you have the same compliance, same change in volume over change in pressure through that whole section until we overdistend the alveoli, and then it takes a bunch of pressure to get them to get any additional volume, right? When we look at compliances, between these two lungs, they were really pretty close. They both had volumes of 1,000 milliliters, there was a little bit of difference in the end inspiratory pressure. But remember, we're looking at change in volume over change in pressure. The change in pressure was from 0 to 19 in this one, from 0 to 15 in this one, right? So we had a situation here where we had a slightly lower compliance. What's a normal compliance of lung and thorax? 80 to 100 mils per centimeter of water. So these are both not real bad compliances. We've got a little difference in compliance there. Look what the change in pressure was. We still had 1,000 milliliters, but alveolar pressure at the end of inspiration in this one went all the way up to 65 centimeters of water. It took twice as much pressure, really, to get that same volume in, right? To get your 1,000 milliliters in. We had a drop in compliance. Now, when we look at expiratory time, it takes less time to get the gas out, because when we look at the time constant, that's equal to static compliance times resistance. So if we have a lower compliance, we have a higher elastance, these alveoli want to empty real fast. We had a situation here where we changed the baseline pressure. How did we change baseline pressure? Well, we had a higher FRC because we did something to the baseline. Maddie? The PEEP thing, yeah, it's a little spring-loaded resistor that they've got to blow against, and then that spring will close it. Andy, who was in here talking about high-altitude medicine and pulmonary edema and all that stuff, I talked about CPAP or PEEP. We're going to do the same thing. We're going to keep some pressure in alveoli, keep some pressure in balloons to prevent them from collapsing. Maybe I'll get lucky and there'll be one with no hole. If I let that thing go, it's going to go empty, right? To keep it from going empty, if I can get around it. You got to keep some pressure in there. That's PEEP. That's end expiratory pressure. So what has happened when I put PEEP on it? What happens to transpulmonary pressure? Goes up, yeah. I'm keeping pressure in it instead of having 0 outside and 0 inside. If I keep pressure in it, there's more pressure inside the balloon or the alveolus than outside. The balloon is not going to collapse. So when we look at disease states, we said you could have obstructive disease, straws, or we could have restrictive disease where balloons don't inflate very well. And we're going to talk about disease states like, let's say, pulmonary edema, where at high altitude, capillaries start to leak fluid. If they leak fluid, that fluid can leak around the alveoli or it can fill them up with fluid. That's a condition called high altitude pulmonary edema. There's other causes of pulmonary edema. But that's going to make compliance go down. When compliance goes down, elastance is higher, they want to empty. We're going to treat that with PEEP. Does that make sense to you? That thing that Andy was talking about, high altitude, I think they're using CPAP to try to prevent that or treat that pulmonary edema. It all goes back to the mechanics of the straws and the balloons, right? Now, in our lungs, if we're diseased, we've got different time constants, different alveoli. So some of them are going to fill fast and empty fast. The ones that empty fast don't air trap. The ones that have a long time constant air trap. But I can only breathe through one main airway. Whatever I do is going to affect these two things differently. This is going to have implications on our gas exchange. So when we get to ventilation and perfusion matching and gas exchange, we're talking about oxygenating the blood, getting rid of CO2, two different situations that are related to breathing for gases. We're going to go back and think, what are the mechanics of the lung possibly doing that screws up my gas exchange? We're connecting all of those dots. Was this helpful? Who else wants to come up and play? I've worked my fingers to the bone to set this up for you guys. Does anybody want to? So, the stuff for the homework, it should be all doable for you guys now. Now, the thing that we had up there in the beginning with Eric was all of the units, and this thing didn't like the units, so we got rid of it. Doing your calculations, pay attention to what the units are, because you guys are becoming Unitarians, right? When you look at your equations or what you're trying to solve for, are you dealing with straws and resistance and flow? Are you dealing with balloons, elastance, compliance, transpulmonary pressure, change in volume over change in pressure? Frame it as one of those two. When we put both of them together, then we're dealing with the time constant. So you guys have done good work today. If nobody else wants to play, we're out of here. And then we'll pick this up again next Wednesday, and we're going to wrap up mechanics next week. And then I think we have exam coming up pretty soon. So probably what I'm going to do is release, there's a little quiz format that you put your homework answers into, and it'll automatically grade it, give you feedback. Then I'm going to give you a quiz. Everybody's quiz is going to be a little bit different because those items are randomly drawn from pools. Everybody's got the same homework problems. Then when you get your quiz done, you'll get some feedback, then we'll go to the exam, which everybody's will be different because they're randomly drawn from pools. So, big football game against a team from down south. I think they're called Bayou. Go Bronchi. All right, you guys are out of here. Have a great weekend. Anybody who wants to play, I can leave it. That's what it's for.
So what would you put the